Started. All right. Hey, everyone. Welcome to week 2's Robotics Fundamentals meeting. I've just started the recording. So we've got, just to start off, a couple of logistical items. In the way of reminders, if you haven't already, I think you should probably be continuing to work on the exercises 1.0, 1.1, and 1.2. Again, we're not trying to get you stressed out about these at all, but this is going to help you complete the rest of things. So, yeah. We've also sent out the week 2 exercises. Also note that in the week 1 exercises, if you haven't finished project 1.3, that's okay. Just use the sort of solution code that we sent out. We also have sent out the week 2 exercises, so if you have finished the week 1 exercises, I would get a head start on those. By next week, we want you guys to work on the Codecademy C++ stuff. That's going to prepare you on references and pointers, which is what we'll be talking about in the next week's session. We also have a couple of RoboJackets videos on ROS and on C++ smart pointers that we want you to watch. Hopefully this isn't too much like watching of things. We'll be sending them out, or they've already been sent out, and you should be able to hopefully just watch through them. Don't worry if you don't get everything from them. We'll be going over a lot of it in the sort of recitation section that we do here, but just putting that on your radar. All right, with respect to pacing, so I sent out a pacing survey last week. A lot of you guys thought, I'm guessing that some of these numbers probably have changed. So a lot of you thought that the week 1 robotics fundamentals on machine learning was way too fast. Yes, it was. We apologize for that. We know it was. We were intending to make it a little bit fast-paced, and then we overshot that wildly. So apologies on that. Hope y'all didn't get too crazy stressed about that or anything. And hopefully you learned something from last week's. That said, most of the other pre-work things you guys said were okay in pacing, so we'll be trying to stick to the same sort of pacing there. The exercises, a lot of you guys hadn't started yet, and I'm guessing that now that a lot of you guys have started those exercises, that little red bar of too much work has probably popped up. So, oh yeah, just as a reminder, practical programming is our Thursday sessions. Robotics fundamentals are our Saturday sessions. So, yeah, we'll be trying to ease your mind on the exercises for sure, because I know that a lot of you were having trouble with those, and there was a lot of work there to cover. So, no worries if you're falling a little bit behind on those. So we've got an attendance link that I've put in the chat. Please, please, please click that right now. We need to record attendance of this meeting. We need to know who is, or not who is here, we need to know how many people are here. So please hit that link. And finally, just as a heads up, I realized that a lot of our information has been everywhere. So we've got one sort of homepage at this point now on GitHub that just lists all of the resources and all of the exercises and explains to you, or shows you where to find all of the things that you need. So I'm going to send this out. I'll send it in the chat as well. This links to all of the, so these are like the GitHub Classroom setup links for everything. And these are all the pre-work, and these are the things. We've also got session playlists, or the playlist of session recordings set up on YouTube for y'all. So that may be a little bit easier to access than the Microsoft Stream stuff that I've been sending out. All right, that's all I've got in the way of logistical announcements. Jason, do you have anything else, or any of the other trainers?
I'll just reiterate the point a little bit more specifically of, we know it's a lot. Nothing that you do here has any effect on what happens later in Robotics except for the skills that you learn. So like if you complete like not a lot of the exercises, but you understand what you're doing, like that's fine. No one's going to look back at these exercises and going to use that in any way, shape, or form past making sure whether or not you understand these skills. So don't approach it like if this is a class. It's not a class. Don't be like, oh, I need to keep up, otherwise I'm going to fall behind. Like, yes, try to keep up because it's good for you in the respect of learning. Don't feel like in any way, shape, or form anyone's going to judge you for being farther behind. Everyone comes in with a wide range of skills that are very different. Some people are ahead, some people are behind, like the average. But at the end of the day, what we're trying to do is raise everyone up to a certain level so you can be more effective in your team later on. So,
oh, sorry.
Go ahead.
So small question. What is the difference between practical programming and programming exercises for for Thursday, for example?
So practical programming is what we've called the Thursday sessions, right? There are also exercises that we send out after practical programming. Those are the practical programming exercises. That stands in contrast to the Saturday ones, which are robotics fundamentals. And then, like, for example, the machine learning sort of workbook that we sent out last week would be a robotics fundamentals exercise. Is that clear?
I think so. So you're saying the practical programming is the actual lesson that's being given or something like that?
Yeah. They're just the names that we're called. Like, we had to come up with a name for what we're calling the Thursday sessions and the Saturday sessions.
Okay.
Those were the best names we could come up with. Hopefully they're not too confusing.
All right. Thank you.
Yep. All right. So does anyone else have any logistical questions before we jump into our main content presentation for today?
Are we going to be putting up the slides on the homepage, the class homepage?
Yeah. I will do that while you are doing this presentation.
Okay.
All right. Thank you, guys. Let me pass it off to Andrew then.
All right. So hopefully you can see my screen. Today we're going to be going over sensors, coordinate frames, and state machines. I'll be covering the sensors and coordinate frames, and then Kyle will take it with state machines and then review the exercises for this week. So before we start, I guess just a short introduction of myself. My name's Andrew Yaravoy. I'm a fourth year mechanical engineering major and CS intelligence minor. I'm on the RoboNav software team, and just random things about me. I did gymnastics for 14 years, and I can speak, write, and read Russian. These are just like some projects that I worked on before for fun at home. So I made like a robotic arm and I don't know what, marble run, I guess that's what we call them. So anyways, getting back into the actual material. So why do we need to know about sensors? Sensors are the main way our robots perceive and react to the world. Without sensors, the robot can basically only do the same task over and over and would have no idea if it succeeded. It would not be able to adapt to the environment. So basically, all our teams use sensors, and today I'm just going to cover the main sensors that all of our teams use. So was there a question? I heard someone say something.
In general, if you have questions, please raise your hand in the chat. That'll help us. Or just ask questions in the chat.
Yeah. Okay, so so just a few of the pictures here. Obviously, the right one's the camera image, and you'll see it's actually detecting features, which we'll talk about a little bit later. The left is the Lidar data, and the middle image is the IMU. So we'll start with the IMU. It's probably the most common sensor that our teams use, and most of our robots have at least one, if not two, IMUs. And so IMUs stands for Inertial Measurement Unit. And it's actually a combination of multiple sensors that help us measure accelerations and orientation. So they come in a really large range of like cost and performance. So they all do the same thing, but they can cost anywhere from like a couple of dollars to several $1,000s, depending on how accurately they measure their orientation and how well they can keep trajectory estimates and stuff like that. So so this is what like the sensor, for example, for RoboNav looks like. It's a Yoast Labs sensor. IMU, and this is the kind of data you might expect to get from it. It just So we'll talk about it a little later. So like I said, it's a combination of sensors. So the first sensor that's included in an IMU is a gyroscope, and usually there's actually 3 of them, one for each axis of rotation. And these help the IMU measure angular velocities. So it's basically how quickly is the sensor rotating. And by integrating angular velocities over time, you can get a relative orientation. So that can tell you like you turned 45 degrees, but it doesn't give you an absolute orientation. So you don't know like if you're facing up or down if you don't know where you started. And also over time, this estimate will, it's susceptible to drift, which means that over time the errors build up and you get a bad, like your estimate will be pretty bad if you just used a gyroscope. Then there's the accelerometer, which, as kind of the name implies, it measures accelerations. And these are linear accelerations, so just like how fast are we accelerating in the x direction or y or z. And again, there's usually 3 of these because there's 3 coordinate directions. We can integrate it twice to get relative position, but whenever you integrate, you kind of noise builds up, and you essentially, it's not a great way of doing it, but it is one thing you can do, and typically we do this in combination with other sensor data to get position estimates. And also a really important part of accelerometers is that they help you measure the gravity vector, which gives you an absolute orientation in terms of roll and pitch. And what I mean by roll and pitch is, if you look at this diagram here, so there's our roll axis is kind of like it's along the x if it's rotating along the x-axis, and pitch is along the this y-axis here. So it won't give you yaw, but because you can tell the gravity vector, which would be this vector here, you can tell how you're oriented in terms of pitch and yaw, roll. So yeah, and these are just some diagrams of how they kind of, like what internally how they kind of work, but you don't really need to know that, so don't worry too much about that. And lastly, there's a magnetometer, typically in the IMU. Sometimes there's even 3, but the magnetometer acts just like a compass, and it measures the magnetic fields and can give you a relative estimate of like what is north. It gives you an absolute yaw measurement. So since now we have roll, pitch, and yaw, you can see why IMU kind of has to use all 3. And it is a very noisy sensor typically, and like it's susceptible to stray magnetic fields. So if you have a motor near your IMU, that's going to completely destroy your magnetometer readings. Also, just like steel structures around you can skew the magnetometer and make it think that you're facing a different direction. So magnetometers particularly are kind of unreliable. But it's important because it gives you that absolute yaw measurement that we want. So combining all 3 of those sensors, you get what is called an IMU, and it's basically this tiny board like this, and you'll have an accelerometer, a magnetometer, and a gyro, and DMC just combines them all. So you can see by turning it can tell its orientation, and here it's just showing a cube what it thinks the orientation is. We can also get a short-term trajectory estimate, so like where we moved kind of, but this is usually short-term, especially with like cheaper sensors, because over time you'll accumulate errors, and really this only gives you like for a couple maybe seconds of accurate like trajectory estimate. A lot of sensors, not all of them, but a lot of them will combine actually these 3 sensor inputs and just give you an orientation directly. But usually these are the higher end sensors. If you get like a cheap eBay, I don't know, like IMU, you'll have to do this yourself. And you'll get it as a Quaternion Euler Angles, and we'll talk about what those are a little later. But yeah, that's basically it for IMUs. Another sensor that we often used is cameras, and everyone's had experience with cameras, but although they are a very great sensor because they give you a lot of information, they can actually be difficult to use for robotics applications because you can't just take the image and immediately yeah, so cheap IMUs will get errors. So there's a question in the chat of like, will cheap IMUs get errors over some time? They'll get, for orientation, they will have more noise, but they won't like drift, so the error won't get worse over time. For like trajectory, definitely, it'll be typically worse. Yeah. So back to cameras, I guess. Yeah.
Right.
Yeah.
There.
Go ahead, Kelly.
Eventually, IMUs will not give you correct orientation. So for yaw specifically, right?
Yeah, for yaw. But
you've got a constant. You always know exactly where down is. You're able to get pitch and roll, right? But the direction that gravity is pointing doesn't change depending on the heading that you're at, if that makes sense, right? Because that's just going to be a top-down rotation, which doesn't change gravity relative to you. So you need to use some other type of sensor, sometimes a magnetometer or sometimes some other sensor if you want to maintain absolute angle or absolute heading in the yaw direction.
Yeah, and a lot of IMUs do come with a magnetometer, but there are some that don't. So, but yeah, and it isn't exactly like a greater cost is definitely better. It's kind of just depends on the IMU, but in general, like a more expensive IMU will be better with like we'll have less drift over time. So, yeah. So back to cameras. So yeah, it can be difficult to extract information, and we typically use computer vision techniques or convolutional neural networks, as Jason talked about in last lecture, I guess. And we typically use that to extract actual information from the camera sensors. There's also, once you've extracted features, you can actually track those features, and from that get your like trajectory. So you can actually track your robot using cameras, the position of your robot using cameras. And this is like often used in like VR headsets. If you've ever used one of those, you'll notice they have like a bunch of cameras on the front, top, or like they'll have cameras on the sides that actually help track your position. Yeah, and we typically use them for line detection, especially, and obstacles detection sometimes. There's not many other ways of tracking a line, so that's, I think, the main use for our teams. I think RoboCup also uses them to track a lot of their robots because they have an overhead camera. I might be wrong about that one. So there's a lot of different types of cameras actually, and different camera setups. So the one you're most familiar with probably is RGB. That's just like the camera in everyone's phones. It's just takes a red, green, blue color image. But there's also some cameras that directly give you black and white. Oftentimes, even if we do get an RGB image, we'll turn it into a black and white image because it's easier to process. But sometimes we don't. There's RGBD, which if you've ever used a Connect, is what it actually uses, and that stands for like red, green, blue depth. So it'll actually give you a depth reading as well. And these were, I think, quite popular like a while ago, like 10 years ago or something. But now, I mean, they're still used a lot for robotics, but I don't think any of our teams use it. Then there's stereo cameras, which is just two cameras that are a set distance apart. And from a stereo camera setup, you can actually get depth as well, because just like your eyes, well, you'll have slightly different images, and you'll be able to tell the offset between features and use that to estimate depth. There's infrared cameras, which is kind of rare to use, but it's basically sees typically like you'll see temperature of things, which I don't know if that's super useful here, but and then there's fisheye cameras, which is and also like there's 360 cameras, which give you a larger field of view but give you more distortion, so it's harder to process them exactly, like the information that you get, but you get more information, or at least a larger field of view, so you can see more at one time. And this is just a quick video from Robo Racing and their robot. You can see them tracking the lines, and I believe they're using OpenCV and just yeah, so they're not using a neural network to do this, I think, and they're just tracking the lines and using that to stay within the track. This is another video from Robo Racing, and you can see them tracking cones and detecting obstacles using a camera, and their robot's able to navigate through the course without crashing into the cones. So, and like I said, you can also extract features, which are these blue or yellow, sorry, circles here, and it tracks the position of these features through the image, and that way you can actually get an estimate of where you are in the world. I don't think any of our robots are currently doing this, but yeah, this is a thing that's quite common to do in a lot of like industrial robotics. So GPS. Yeah, iPhones, they use RGBD for face detection. I do believe they do that. Yeah, I think they use. Are they the ones that I think they project the image on your face and then they actually read the pattern. So yeah, they are doing RGBD for that. So yeah, so another sensor you'll often see is GPS. So GPS uses satellites to localize itself. So it knows at every second, it knows the position of all the satellites that are in space actually, and then it gets a signal from them and measures how long it takes for that signal to arrive at the to the sensor, to the receiver, and using that time and essentially the speed of light, it does some calculations and figures out its position in the world. What you end up getting is your longitude and latitude as well as an altitude. So it'll look something like this, where it's just like a really, it's either using degrees and then like minutes and seconds, or it's using just like a decimal representation. But essentially it represents your position in the world, and there's a way to convert from a global coordinate system of like longitude, latitude to a local coordinate system where you could just say where you started 0, 0 and track your position from there. So the advantages of a GPS is that it gives you an absolute position. So that's actually really rare to get an absolute position in the world. That's a really nice feature of it, and also it's relatively cheap and pretty easy to use. The issue is you get infrequent updates, so you only know your position every maybe to like 10 times a second, maybe one times a second, depends on the GPS, but it's not that often, and for a robot, a lot can happen in a second. So another thing is, a big thing is that your accuracy for a regular GPS is quite bad typically. It's like, it can get better than 4 meters, but it's just like, it can also be like 40 to 50 meters. If you ever used your GPS on your phone, you know that like obviously you get that huge circle at first, and it takes a while for it to really figure out where you are. So in terms of accuracy, if you want a much more accurate estimate, what's often used is a real-time kinematic or RTK GPS, and it's basically, it uses stationary reference station, or sometimes even multiple stationary stations that are able to average GPS measurements to get the station's precise position. And then the robot actually sends, it receives it measures the phase of a signal that the stations are emitting, and using that, you can get like centimeter level accuracy. This is often what's used if you want like really accurate position estimates. The only thing is you need a tower, like you need to have that station, so it's extra setup, and also they're typically more expensive than just regular GPSs, so it's there's that. And some teams are allowed to use them and some are not, so so yeah, so I think well, a lot of our teams use GPS especially, and I think Robo Racing is gonna use is RTK? I'm not sure. Oh, it's not. Yeah. Okay. Yeah. I think for one of their competitions they were considering at least using RTK, but yeah, RoboNav and Robo Racing use GPS. I think. I know definitely RoboNav uses GPS. So another sensor that you'll almost definitely see is encoders. And encoders just measure the position of of essentially a shaft or a motor, and they do that by, well, there's a lot of different ways of doing it, but essentially they measure these steps, and by counting the number of steps that that has taken place, you can tell the rotation. So like each step might be 1/200th of a rotation, or 1.8 degrees. And if you know that you've moved, say, 10 steps, then you know you've moved 18 degrees. And it is kind of a relative measurement because but usually there's some, well, encoders sometimes have a starting point. So it's, you can, after calibration, you can usually assume that you've kind of got your exact, you can tell your exact position. But encoders are often used to measure motor velocities and measure the position of motors. So all our teams use them, and you can use them to get odometry, which is essentially like a rough estimate of how much your wheels moved, and then from that you can calculate what your position change is. Assuming no slip, which is typically a bad assumption. So the last sensor I'm going to talk about is Lidar. This is a much more recent sensor. It stands for light detection and ranging, although no one uses that, and it's always referred to as a Lidar. And essentially what it does is it emits a laser, a laser burst, and it measures how long it takes for that light to return to the sensor. So you'll get something like this plot here, where you'll have like a peak at a certain point, and after you emit the laser, and you measure the time, and then using the speed of light, you can calculate the distance to that point that the laser reflected off of. So originally it was just like using a stationary kind of laser, but nowadays there's a lot of these like Velodyne and Alster pucks. They basically have a bunch of these LiDAR sensors, where usually like 16 channels, or sometimes like up to, I don't know, like there's 128 channels. But essentially they emit a bunch of laser points, and they measure how long it takes for each one of them to return, and then they generate this point cloud. So each one of these little dots is a single laser beam that got reflected and it's keeping track of. And you get these laser points as a point cloud, and using that you can tell obviously like where obstacles are, because you can see them as actual points. So they're useful for detecting obstacles. RoboNav uses a LiDAR. We use a Velodyne puck, and yeah, from that you can track obstacles and avoid them. So this is a video just showing kind of how, this is actually from my internship from this summer, but you can see that a lot of, even in an industry, they use LiDARs a lot, and you can see how it builds a map of the world. Eventually it'll show. But essentially there's a drone flying, and it's tracking its position as well as creating a map of the world using a LiDAR. And this is kind of like what the LiDAR view will look like, where you basically have a bunch of points and you can see obstacles along the way. And combining a bunch of sensors, you can plan trajectories and, well, not plan trajectories, but you can tell where you are in the world and navigate. So yeah. Any questions before I move on? I know I went kind of fast. There's just a lot of material we're going to try to cover today. So if there's no questions, I'll move on to coordinate frames. So one disclaimer, I guess, if you aren't super familiar with matrices, a lot of this is going to be hard to make sense of, especially, well, the math. In that case, just try to get the general concepts. You don't necessarily need to understand all the math. It's not, if you're familiar with matrices, I do recommend just try and follow the math, but if you don't, it's fine. If you ever have to do this, first of all, there's oftentimes libraries that will do a lot of this for you, all the math for you, and then second of all, like you could always look up resources. This is a pretty common thing that's done in robotics. So yeah, starting on coordinate frames. So like, why do we need them? So a typical robot will consist of multiple rigid bodies that are linked together through transformations. And transformations are just essentially a translation plus a rotation. There's other transformations, but those are the only ones that we care about for the presentation at least. And oftentimes the only ones we really care about for physical robots. So we can use coordinate frames to model the state of the robot. And yeah, so let's take example of this kind of Roomba-like robot where it has a front, and so it's facing a particular direction, and it has some translation from some origin that we defined, and then it has some rotation. So here it's translated 3 in the x direction, 2 in the y, and then it's rotated 45 degrees. And usually rotations are counterclockwise. That's just like a common math convention. This inertial frame, by the way, is probably going to be your map. So if you're generating a map of the world, wherever the robot starts, it's probably going to be 0, 0. And over time, you want to track where your robot is relative to where you started. With coordinate frames, we can basically describe this image here as just two coordinate frames with a transformation in between. So yeah, so frame 0 here is the inertial frame, which is your map, and frame 1 is your robot, essentially. And this is a very simplified robot, but yes, and this is also in 2D, but we'll get into 3D a little bit. It's pretty much the same. So the first questions that need to be answered is what this transformation looks like mathematically, and why do we prefer to use coordinate frames over like just keeping track of these like translations and rotations. Well, yeah. So why we use what this transformation looks like is essentially a matrix where you have a rotation matrix, which we'll get to what that is in a second, up top. Then you have a translation vector, which is how much you've moved. The rotation matrix describes how much you've rotated. And then you have 2 zeros down here, and then a 1. So it's just how you describe it. There's nice mathematical properties that come out with describing it in this form. So a translation vector, like I said before, it just tells you how much the robot is translated. So for example, if we moved +3 in the x direction and -4 in the y direction, a translation vector would look like this. So it's just 3, -4. So a rotation matrix, what is it and why we use it? So a rotation matrix is a matrix that expresses a rotation about the origin without scaling. In 2D, it looks like this. So you'll have essentially, yes, linear algebra time. Yeah, so you'll have a cosine theta, negative sine theta, and cosine theta, and this is just a 2 by 2 matrix. And the theta describes the angle that the rotation, it's how much you rotated. So this vector, for example, is rotated by 45 degrees. So you'd plug in 45 degrees for theta, and you'd get a matrix that looks like this. So this just shows that you can rotate this vector with a rotation matrix by just multiplying the actual vectors. So this is 4 in the x direction, 0 in the y. And if you multiply by the rotation matrix, you get a new vector that is rotated by 45 degrees, as we would expect based on the theta we inputted. There's going to be, it's a lot of math. Don't worry too much if you're not super comfortable with it. It's like I said, there's a lot of packages that will do this for you, but understanding what the transformation is at least is nice. Like understanding this form here. Looking at coming back to transformations, transformation matrix for the original example where we had the robot move 3 over, 2 up, and then rotate by 45. Would look like this. So we have the rotation matrix in here in the top left. We have the translation vector in the top right, and then we have 0, 0, and 1. So this is the transformation that, it transforms from the coordinate frame 0 to 1, I think. I might have got that backwards, but yeah. So why do we use transformation matrices and coordinate frames? It's because they allow us to easily figure out where every point on the robot is in every different frame of reference. So say we know that the nose of the robot is 1 unit from the center of the robot. And this coordinate frame, it's just tracking the center of the robot. That's what, this is lined up with the coordinates here. So if the nose of the robot is 1 unit from the center, we want to know where is it in the map. So where is it in this inertial frame? We could tell that it's not going to be at 3, 2. It's going to be slightly farther up. But how do we figure out that point mathematically? And it turns out with coordinate frames and transformation matrices, it's very easy. You essentially just take the point that we know in our robot local frame. So we know that it's if this is 0, 0 here in the middle, then that point would be at 1, 0 because it's 1x and 0y. And then to convert it into the initial frame, we convert it into what is called a homogeneous vector, which is literally just adding a 1 at the bottom and making it a 3 by 1 instead of a 2 by 1 vector. And so we add a 1 at the end and then multiply by that transformation matrix that we calculated earlier. And what we get is the actual, the position of that point in the inertial frame. So you can see after multiplying, we get this value, and logically this makes sense. Where this is. So you'll get a 1 at the bottom here. You basically just ignore that, and the top 2 values are going to be your the point. We can also have a situation that's kind of in reverse. So if we know that we have an obstacle, we will typically know that the obstacle is a certain point in the map. But sometimes we want to know where that robot will see the obstacle. So if this is what the situation looks like, you have a robot and there's a point behind it that it might be sensing somehow. And we want to know in the robot's coordinate frame, where will this point appear? So it's kind of like we're rotating, and this is our now 0, 0, and we want to know where this point is. Once again, this turns out to be very easy with transformation matrix, because all you have to do is invert the transformation matrix and multiply by the point just like we did before. So that point was at 1, 1 in the inertial frame, or frame 0. And so we just add a 1 at the end. We invert the transformation matrix that we had earlier. And then we multiply it to get the new the position of that point in the robot's frame. So this, if a robot had a sensor that's sensing this point, this is where it would sense it, not at 1, 1, because that's where it is in the map. Yeah, so yeah, and this would usually represent your local coordinate frame, and this would be your global coordinate frame, so like the inertial frame. And oftentimes you need to be able to transition between the two, so this is why we use transformation matrices. Okay.
So we had a good question. Check the chat or.
Yeah. So is it just the
local and global?
Both local and global coordinates could be useful for specific tasks. Do you keep track of both? Yes. So oftentimes your sensor readings will be, you do keep track of both coordinate frames, coordinate systems. And oftentimes your sensor inputs will be coming in your local coordinate system, or like your robot frame. And then the map that you're trying to build, if you are building a map, will almost always be in a global coordinate frame like this inertial frame. And so you do keep track of both, kind of, although the inertial frame is kind of your like reference, so it's not so much you keep track of it as it exists. but yeah, you do keep track of where your robot is relative to this coordinate frame, and that's called localization, and it's actually a topic we'll be covering later. Another thing is we could do a lot of the stuff we just did like manually, kind of, but the really nice feature of using coordinate frames and transformation matrices is that once you have more than one, it's still very easy to keep track of how you get from like one coordinate frame to another. So here, for example, we have a coordinate frame. And, well, so let's say the robot has like a robotic arm or something. That would have its own coordinate, the end effector of that arm would have its own coordinate frame. And we would want to keep track of that as well. And so if, say we have a sensor on the end of that arm, like if it senses something and we want to transform it into a map, now we have this like chain of coordinate frames. So you can see you have like an arm and it goes into a robot and then it goes into inertial. Sometimes you'll see it go the arrows point the other way, but all that is just the inverse of these transformation matrices in that case. And there's some useful properties of transformation matrices that make this easy. So one is that if you have a transformation matrix that goes from coordinate frame 1 to 0 and a coordinate frame 2 to 1, you can just multiply them together and you'll get 2 to 0. So like essentially it's like 2 to 0 would mean that if you have a point in your coordinate frame 2 and you multiply it by this, you will get the position of that point in coordinate frame 0, which is your inertial frame. Hopefully I didn't confuse people there, but it's just that it's easy. Like mathematically, it's pretty simple to move between coordinate frames, even when you have multiple. And this is just a property they have to be careful of if you have two transformation matrices and you multiply them together and you want to take the inverse, it's actually equivalent to, you have to flip the order if you distribute the inverse. That's something that you can get caught up by if you're doing math by hand, but yeah.
Hey, I have a question.
Yep. Great. What's the question?
Yeah, I actually did raise my hand. So, just to get the understanding correct, is the inertial frame sort of like the very first like global frame, or is it the local frame of the robot, or is the global thing different?
So the inertial frame is typically where your robot starts. That'll be like 0, 0, and whatever direction it's facing, or sometimes you'll use like north as your direction, starting direction. Is just like, that's the point in space, and that's just like your inertial frame, and that doesn't move. So as your robot moves, that point will stay in that spot that you started at.
Okay.
So just as a note, your inertial frame can be like as long as it's fixed and doesn't move, it can be any fixed frame. So the navigation teams, so RoboNav and RoboRacing, use that convention, right? But RoboCup, for example, would use the convention of the field is the inertial frame, because all of the there isn't one place that all the robots started, right? We have to keep track of all of the robots relative to a single inertial frame. So it sort of depends on the
Understood.
Okay.
Okay.
Yeah, it depends on the application. Just the zero is kind of like just like if you have no no discrete point that you can pick for it. But obviously, if you have a field, it's nicer to pick a single point. And also, like if you have multiple robots, you want them sharing that frame, like Kyle said. So, yeah.
Okay, thank you. One more question? I apologize. But so
No problem.
all these transformations, right? Can you like assume that they're all being put into homogeneous matrices, so that when you
Yes.
compute the result, you get the coordinates of a particular obstacle or goal or where you need to go?
Yeah, so each one of these transformation is a homogeneous matrix, which is what, oh god, it's this right here. So
Okay.
yeah,
All right. Thank you.
and that's what, when you're multiplying them, that's like, it's literally matrix multiplication. So it's not like there's some weird thing going on. So final note, I guess. So what I said, everything I've shown you so far has been in 2D. But most applications we're dealing in 3D. I guess a lot of times we still represent our maps in 2D, but if you are dealing in 3D, the math is actually almost exactly the same. The only difference is that the translation vector is now 3x1, so because now we have a z direction, and then the rotation matrices, they get a little bit more complicated. They become 3x3s, and this is, for example, rotation about the x-axis and rotation about the y, rotation about the z, and you can combine them to get this rotation matrix here. You also have 3 zeros. Basically, there's just like 1 at the end, no matter what dimension you're in. You'll just have zeros on the bottom row for whatever number of, whatever your dimension size is. So this is like, for example, what in 3D, what a homogeneous matrix will, like, or transformation matrix will look like. So yeah, and in practice you'll have a lot of coordinate frames. So I've been showing you examples of like 3. This is probably overkill. I don't think any of our robots look exactly like this, but you will typically have a coordinate frame for every single sensor you have on the robot, because it's useful for when you're making the map. And then also every like joint or like rigid body that moves relative to another rigid body will have its own coordinate frame. So you do get quite a lot of them, and that's why oftentimes they get represented like this. So they get represented as like I guess this is a flow chart. I don't know, but it's
a tree.
Yeah, it's a tree, I guess. Yeah. So you'll have like each one of these arrows will represent one of those transformation matrices. And if you want to move, say, from like map to chassis, you would multiply them every time that you go in the direction of the arrow, and you would multiply by the inverse whenever you go against the arrow. So from any point here, you can go to any other point just by following the arrows and multiplying by the inverse whenever you're going against one, and multiplying by the transform just when you go with it. Like I said, a lot of this is handled by packages. So like TF2 and ROS is, well, you'll get to that later, but it's basically, it handles all this math for you. And quick note about rotations. So we've talked about rotation matrices, but there's 2 other ways you'll see rotations commonly expressed. They're not really, they don't work with transformation matrices, so you'll have to convert to a rotation matrix if you get your rotations in any other form. But you should know about at least that these other forms of, well, other ways of expressing rotations exist. So one is Euler angles. This is a very common one for like displaying the information to a human, because all of these representations are representing the same rotation. However, I have looking at this, I have no idea what these rotations would be. But looking at Euler angles, you can kind of tell. Yeah. So what you essentially get is the first number. Well, there'll be a certain sequence. It depends on your Euler angles, so you'll have to look this up for a particular application. But usually it's roll pitch yaw or yaw pitch roll. So that's the order that these numbers are coming in. So if it's roll pitch yaw, this means that you roll 45 degrees. Then from that starting point, you pitch. You pitch 50 degrees, and then you would yaw negative 10 degrees. So the advantage of this is you can actually kind of visualize what this rotation would look like. And so oftentimes when it's displayed to a human, this is like the way it'll get displayed. But the issue is to do any sort of math is really bad, actually, with Euler angles. There's a lot of problems. Like the math calculations themselves get kind of messy, and then also don't really need to worry about gimbal lock. But basically, you'll get weird things when you try to move continuously through Euler angles with Euler angles. So you don't want to use Euler angles whenever you're doing math. So you saw rotation matrices; those were pretty good for doing math. Another form is Quaternions. And this is often used if you're only worried about rotations and not like translations as well. So this is a 4-dimensional coordinate system where essentially you'll have a real part, which is like a W, and then you'll have X, Y, Z. Yeah, so complex numbers to the revenge. It can be thought of if you want to, and it is this basically, where it's a complex number, but instead of having just one imaginary part, it has 3. So it sounds very hard, but in reality, it's actually really nice mathematically to work with. Essentially, all you need to know that there's 4 values in a quaternion, and they represent a rotation, and they completely define the rotation, and the math with it is pretty easy. If you know how to do it. I'm not going to go into the math of it, but there's a video by 3 brown, 1 blue, which talks about some of the math and gives you a really nice visual representation of what's going on, much better than I can do. So yeah, but the issue is it is hard to visualize for humans and to reason with, really. So yeah. Oh, 3 blue, 1 brown. I'm sorry. Yeah. Anyways, yeah, and that's it for me. I'll hand it off to Kyle now. If there's any questions, I should answer those. But.
All right. Thanks. We're gonna talk now about state machines, and I'm actually gonna.
Yeah.
Just because there's a lot of transitions, and by the time we're done with this presentation, you'll get the pun that I just made. Okay, so can everybody see my screen? Hopefully. We'll go with yes. So far we've talked in the sort of realm of C++ about how you do your normal program flow, which is you have a sequence of instructions and your program sort of goes down in a line, right? You execute one instruction and you execute another, and you might have ifs and whiles and etc., right? Plenty of things that make that control flow more complex. But in general, things move in a straight line in your program, right? So there is a beginning to your program and there is an end to your program. This is not really how robotics works. In robotics, there may be a beginning, but basically everything you're actually doing is in the middle and there's no end to your program. Your robot is going to be running for an arbitrary amount of time. You don't have a set list of things that you need to do. You are just running a robot. So you'll often see this described as the perceive, reason, act cycle, which is where you can think of it as a while loop, right? Where you just forever, you repeat this sequence of reading things about your environment, right? Thinking about those, making some decisions, and then applying those decisions, and then waiting a cycle to do the whole thing over again, right? And this is sort of, it makes sense with how we intuitively think about what you need to do. You need to see the world, you need to think about it, and you act, and that happens constantly, and it's repeatedly happening, right? But it is very different from how we might have so far have written our programs. In general, there's a lot more I can say on this, but it's sort of just serving as a motivator here. So state machines are one way you can address this for certain types of things. So as an example, right, if you are just writing sort of code in the program way, like the programming way where you're doing a sequence of function calls, essentially, right? You might say, okay, you might call a function that is move to point goal, right? And then you might raise your arm afterwards, right? You might say you have an arm on your robot, raise that after move to point. Great, it can do that. But what if you want to move your arm while you're driving to that point? Do you write a new function that's called like move to point while raising arm? Do you handle all the possible cases there? That's a bit of a pain, right? And there are a lot of ways to address this. Usually what you would do is have your actual subsystems where you're doing things related to the arm and related to the drivetrain, have those separately and have those sort of each have independent cycles. However, for the sake of exposition here, there's another way that you can do that, and that is state machines. So, for example, you might start in a state where you are waiting for your goal. Let's see if I can get the pointer on. So you might start where you're waiting for your goal, right? Once you get a goal, or once you get something to do, you can move into any one of several things. You could only be having to move your arm. You could only have to move your drivetrain, or you could have to move both at once, right? And transitions along this might represent when you complete a goal, right, or when you get a new goal. And then finally, when everything is done, it can all transition back. So this is an example of something called a state machine, right? And in a state machine, you are in one state at any given time. That's one of those boxes, right? Now you want to repeatedly, basically every one of those cycles we were talking about in the reason step, you want to be updating your state based on new sensor inputs, right? And based on decisions that you might make about the environment. Then you want to choose transitions based on those sensor inputs that basically gives you the next state that you'll be in. Now, sometimes that next state is the state that you're already in, and sometimes that will actually represent a change of state. So here's a less, we'll say less contrived example, because this is actually something that shows up in code. For reference, RoboCup uses state machines a lot, so that's sort of a reference point that I'm using for this presentation. So when a RoboCup robot wants to do a pass between two robots, right? You might sort of follow this general sequence of steps. And in the nominal case, what it will do is it'll choose a pass, it'll align to the pass, it'll kick, and then the receiving robot will be responsible for receiving that pass, right? And that's coordinated all sort of on one central place. The thing that state machines allow you to do in this case is give you a very easy way of handling what happens when one of those steps fails. So for example, if you fail to align, that's probably because another robot is blocking your pass, right? So you might want to adjust your pass. If you fail to kick, that might be because of an interception, right? And similarly, if you fail to receive. So that's a specific RoboCup example, but hopefully that's a little bit more illuminating on why state machines might be a useful concept for us. Now I'm going to give a quick overview, just a run through of one of the assignments for the sort of next week's worth of things that you're going to be looking at. Don't stress about too much about this. It's got some thinking on it, but it should be hopefully interesting, and it should get you to think a little bit about how to use these. So in this sort of problem, we're saying that there is a intersection, right? This is my crudely drawn intersection. And you are in charge of controlling these 4 traffic lights based off of time and based off of a sensor here and a sensor here that tells you whether a car is here. Now, there are a couple of very simple rules for this. It operates in cycles, so you might do let the road pass in one direction and then let the road pass, or let the other road pass, right? And you'd repeat that. You want to be doing yellow lights between green lights, and green lights should be on for 5 seconds. So I'm just going to walk through what this might look like. You might have a countdown, right? And you are waiting for that countdown to end before you exit this green light state for the east-west road. Right? Then at the end of that countdown, you might see that there is a sensor, in fact, tripped on this north-south road. So that means that we want to change the lights, and we change into a temporary everyone red state before changing the lights back to green, at which point we can keep going. So, so you'll count down again, right, from that green state. And then here, now we don't have that sensor blocked, so we can actually let that one pass. There's no need to change the lights here, so we can stay green. This is like a very brief explanation. In general, there's a longer write-up that's set up for you guys. But we're going to ask you in the group discussion sections to talk a little bit about this. All right, that said about group discussion sections, let's break out into group discussions. So hopefully you guys all know which group discussion you should be in by now. Let's just jump into that. I'm going to be in RoboCup group discussion today, so please, hopefully you guys don't have any questions. Jason, could you stay in the main discussion, in the main room for a little bit, just to answer? Okay, great.
And also pop around, so don't worry about it.
Great. All right. See y'all in the main discussions then.
Sorry, I was out for 2 seconds. If people were talking to me, I didn't hear. Although it seems like everyone is out of this channel anyway.